Good afternoon, and welcome to our third week of Faculty Perspectives. At this point in the summer, it's important to remind you of the requirements for these sessions to stay on track to complete introduction. In order to complete the basic requirements for introduction, students need to watch live or asynchronously 10 faculty perspectives of your choice and complete the reflection assignments on the community.uoregon.edu site for the entering class. Students who wish to earn 1 credit over the summer must select 20 faculty perspectives by first completing 2 full faculty perspectives tracks, that's 16 of the 20 total talks required, then select 4 additional faculty perspective talks from any of the remaining tracks. Complete your post-talk reflections for all 20 of the selected talks, and then complete 1 comprehensive summary reflecting on your learning from the tracks you completed. You can find these details in the community.uoregon.edu course for the entering class. As a reminder, for those students who are watching in Zoom live right now, we will have the presenter in the last 15 minutes answer your live questions. So please use that Q&A feature at the bottom of your Zoom screen so that we can answer your questions live on camera. At this time, I'm pleased to introduce our third presentation in the Environment and Climate Change track. What do we need to learn about the Earth to be more prepared for earthquakes and mitigate the risk they pose? Earth Sciences Professor Valerie Sahakian tackles this question right now. How are you, Dr. Sahakian?
I'm doing great.
I'm going to turn things over to you.
All right. Thanks. So as Cora said, I'm going to talk about what do we need to learn about the Earth to be more prepared for earthquakes and to mitigate the risk that they pose. Before I start, a little bit about me. I am an assistant professor in the Department of Earth Sciences here. My pronouns are she, her, hers. I am mostly a geophysicist and a seismologist. My PhD is from geophysics from the Scripps Institution of Oceanography. Outside of work, I love learning and reading, and I also really like trail running, climbing, surfing, and pretty much anything that gets me outside in the water and touching the rocks and the things that I study. And I also really love playing with my cat and my dog, and one of them is on the picture on the left there. And before I get going with the question that I posed at the beginning, I want to mention that the Pacific Northwest does experience earthquakes, so we might not feel them frequently, but they do happen here. So I am putting the question out there, do you know what to do if you feel shaking? And if this were in person, I might have you get down and drop cover and hold on. So this is just a reminder that if you feel shaking, this is one of the best things that you can do to keep yourself safe. And so what I'll talk about today is why do I and should you care about earthquakes and the Earth? What is an earthquake? The main question, which is what do we need to learn about the Earth to be more prepared for earthquakes and to mitigate the risk that they pose? How else are earthquakes a lens for studying the Earth? How else can we use them for studying our Earth? And then how did I get into this? What kind of skills are used and what opportunities exist here at the University of Oregon in Earth Sciences? Why do I and why should you care about earthquakes? And when I bring this up, I usually show these 2 tables. The first one is the top 10 deadliest earthquakes since 1900. And this is a table where I have the magnitude of the earthquake, the casualties, the name, the place, and the year it happened. One of the things you'll notice on this list is that the first one is pretty big. It's a magnitude 9 to 9.3, and this was an earthquake that happened in December 2004 in Indonesia. The casualties listed for this are actually, a large number of these are probably from the tsunami that happened afterwards. But what you'll see is that for the rest of the earthquakes on this list, they're mostly in the magnitude 7 range, and they have about the same number of casualties related to them. So maybe in hundreds of thousands. The top 10 largest earthquakes since 1900 are on this table. This is the same thing where you can see their magnitude, casualties, name, place, and year. And on the left-hand side, you can see that the magnitude for these is quite a bit larger than the magnitude for the earthquakes on the last slide. So one thing that's really interesting is that a magnitude 9 earthquake has 30 times as much energy as a magnitude 8, which has 30 times as much energy as a magnitude 7. So that means that these earthquakes on this table right here are quite a bit larger than the ones on the last table, yet some of them have no casualties at all. And why is this? To start to answer this, I put this on a map here. The top 10 most damaging earthquakes are marked as red diamonds on this map of the world, and the top 10 largest earthquakes are mapped as blue circles. The first thing that you'll probably see is that the blue ones happen in this area that we call the Ring of Fire. This is this area around the Pacific Ocean where we have a lot of large earthquakes, and it's because we have a lot of tectonic activity and a lot of subduction zones. This is where we get really big earthquakes. But the most damaging earthquakes don't necessarily occur in the same place. And where are they occurring? Why is it that these are more damaging when they're not necessarily the largest? To make that a bit clearer, and maybe you've already sort of guessed this by now, I put this on top of a map of population density. The black colors are very dense population, and the light colors are very low population density. And what should pop out to you is that the top 10 most damaging ones occur in areas typically that have very high population density. The lesson learned here is that there's a difference between risk and hazard. So there's a difference between the effect of an earthquake and how it affects us as society and humans versus the hazard, which is how frequently do we expect shaking, or what are the earthquakes, what's the earth doing? As some definitions, when it comes to earthquakes, hazard is the expected frequency of shaking, meaning how often do we expect to feel strong shaking in a particular location or moderate shaking. Risk, on the other hand, is the exposure to harm, danger, or loss. Risk and hazard are not the same because risk is a combination of hazard. So in areas where you have a higher expected frequency of shaking, you'll have more risk just because you can have higher or more frequent shaking. But it's also a function of exposure, which is the number of people or assets in an area, as well as vulnerability, so the percentage of losses from shaking. And that means that if we want to mitigate risk in earthquakes, we need to control the second two in this equation, so to speak. So hazard is going to be constant on human timescales. The Earth will do what it wants to do, and we can't change that, but we can do more to change the percentage of losses from shaking. So we can make our infrastructure better, we can design our buildings better, and we can be more prepared. And this is how we reduce the risk. Just to show a couple examples, Japan is an area that has very high seismic hazard because they have large earthquakes frequently there. But in 2011, there was a magnitude 9 earthquake that happened there. The tsunami was very destructive, but for the earthquake itself, there was a lot of shaking, and there was very little damage to their infrastructure and such from that shaking because of the fact that they've designed their structures so well. And you can compare this to a couple more recent earthquakes that are smaller, almost 30 to 100 times smaller. So the Nepal earthquake, which was a 7.8, and the Haiti earthquake, which was a 7.0. And you can see there's a lot more damage from these, and that's because of the vulnerability here. So the exposure and how structures are designed. And so the reason that we should care about earthquakes is that we can actually do something to be more prepared about these. So we shouldn't necessarily be scared of these. We just want to make sure that we're more prepared. And in order to do that, the best thing that we can do is understand more about them and what their hazard is. So where do we have earthquakes? How big will they be? How strong will the shaking be? And then we can use that to make ourselves stronger as a society. And so one answer to this is that the more we learn about them, the better we can mitigate risk. And in addition, there's the fact that we also have them here where we live in Oregon. And so this shouldn't be something that's scary, but just think about it in terms of how can we be more prepared for these. This is an article that came out a number of years ago in the New Yorker that I think brought attention to the fact that we can have large earthquakes here, and we just don't have them all that frequently. And I think one of the really positive things about this article that came out is the fact that a lot of action has been taken since then to make us more prepared. The next question is, what is an earthquake? An earthquake is the sudden release of stress, which was created by motion between two tectonic plates. And I have a cartoon here from the USGS that shows a subduction zone, which is where you have an oceanic, this is sort of like our subduction zone here in Cascadia. You have an oceanic plate with oceanic crust that's subducting beneath a continent. And that's because this oceanic crust is a lot denser than the continent. So when it meets the continent, the oceanic crust is what sinks. When this happens, you have two tectonic plates that are constantly rubbing against each other. There's friction between them, and so stress is built up. And this is happening on the order of hundreds of kilometers. So in our case, this is happening from Northern California up to Canada. So this is a large area over which you're building stress. Eventually, our Earth's crust isn't strong enough to hold on to this stress, and so it will release this energy that has built up in the form of an earthquake. We have a lot of different types of earthquakes here. So one that you might think about a lot is the earthquake that happens at that boundary between the oceanic plate and the continental plate, and those are called subduction zone earthquakes or megathrust earthquakes. And in particular, in the Pacific Northwest, the last one that we had here, the last large one, was in 1700. We think that was a pretty large earthquake. But we have a lot of other earthquakes here. We have these things that are deep earthquakes. So these are earthquakes that actually happen within the oceanic crust that has already subducted. And then we have crustal earthquakes. So these are earthquakes that happen on the continental crust, so on the overriding continent. And these earthquakes affect us differently because they are different sizes. Some of them are closer to us and some are farther away. And so the hazard that they pose, or the expected frequency of shaking, is a little different. So the best thing that we can do is try and understand what is the environment that these are happening in so that we can be more prepared. And this brings me to the next question, and the main one, which is what do we need to learn about the Earth to understand earthquakes better and then mitigate the risk from them? And the first thing here that we need to know is where are the faults? So where are these areas where stress is being built up and where you can have earthquakes? We know now that there's a subduction zone here, for example, in Oregon, which is what I'll focus on today. And so we know that there are earthquakes there. We know that there are these deeper earthquakes in the oceanic crust, and we know that there are these earthquakes in the continental plate. So that's a plus. But these earthquakes happen on a number of different faults. So one thing that we can do to be more prepared is learn about where these faults are, actually go out and find them. And then once we figure out where they are, we would like to know what size of earthquake can they create and how often do they make that size earthquake. The ways that we do this, there are many ways that we do this. So one of them, for example, is looking at our landscape. So oftentimes with faults that happen, say, on the continental crust, we can actually see them in what our landscape looks like because they've changed the surface of the Earth. We can use seismic data, so we can look at little earthquakes to see where little earthquakes happen, and that probably means that there's a fault there that's building up stress. We can look at it with imaging data, so these are tools that we use mostly with seismology, where we can actually look into the Earth and image what that looks like as a cross-section, so we can figure out where the faults are. And then we can also actually go and touch them and put our hands on it. So the top left picture is showing a trench. So this is something that when we know where a fault is, we dig a trench across it, perpendicular to it, and then you can actually see where the different layers of soil and sediment have been moved. You can measure how much they moved, you can date that soil and sediment, and then you can learn about when earthquakes happened in the past and how much they moved the Earth at that time. And that is one of the things that helps us figure out what size earthquake can these faults create and how often. Other things we can do is we can use GPS. That's that bottom picture there from EarthScope. That's a permanent GPS station in the San Francisco Bay Area. And these GPS are very high precision versions of maybe what you have on your phone. So we put these out on the surface of the Earth, and they sit there for on the order of decades sometimes, and they measure the very slow movement of the Earth. By measuring this movement of the Earth, we can figure out where stress or strain is being built up, how much is being built up, and what that means about how much energy is being stored essentially on that fault that might be released. There are other more subtle ways that we can learn about earthquakes. On the top right is one of the first things that came out to actually figure out that we had a subduction zone here in the Northwest. This is the famous Brian Atwater, who's a scientist at the U.S. Geological Survey. And he figured out that we have large earthquakes here because he started noticing tsunami deposits along our coastline and figured out how old these were. He figured out when these tsunamis occurred, and that means that they probably occurred from earthquakes along our subduction zone. So this is one way that we can learn about past earthquakes, is through the things that they affect. So for example, some of them make tsunamis. On the bottom left are sediment cores. When an earthquake happens in the offshore area here, you shake a lot of the sediment in the bottom of the ocean floor, and that sediment will move, sort of like in a submarine landslide. And all of that sediment gets carried down a slope, and then it gets deposited and makes these very specific things called turbidites. So these look like sand mixed in with a lot of clay in the bottom of our seafloor. And what we can do is actually go out on a ship and collect sediment cores of what this looks like. So that's what you see on the bottom left, and identify where these turbidites are, how deep they are, and how old they are. And using those, we can figure out when earthquakes happened along our margin or in our area, and how big and how frequently they occurred in the past. Another thing that we can do is we can use what's called dendrochronology. So that's what I have this tree ring here for. Earthquakes on our coastline often make the coast subside, and when it subsides, trees that were living there all of a sudden become drowned and they die. And so what you can do is look back at these things called ghost forests. So Nescoen Beach is one example of this. You can go and find all of these submerged tree stumps that all of a sudden died very quickly in an earthquake when the coast subsided and went down. And because we can count the tree wings, we can figure out how old that tree was when it died, so when it was drowned. And then we can also date them to figure out when that happened exactly. So these are all different tools that we can use to figure out where faults are, what size earthquakes they can create, how often and when they happened in the past. And this is really important to help us understand seismic hazard. Once we know all that, remember that the expected frequency of shaking is how often do we expect to feel a certain amount of shaking. So it's not just where the faults are, but it's also how much shaking can they create. So now we need to know when there is an earthquake, how strong will the shaking be from that earthquake, what makes shaking stronger or weaker, and what things about the Earth and the Earth's crust can control how strong shaking will be. So for example, the larger the earthquake, the stronger the shaking. The closer you are to the earthquake, the stronger the shaking. But there are also a lot of more nuanced things and properties about the Earth that control this. So for example, the soil and the sediment of what you're on can sometimes make shaking stronger or weaker. The material and the Earth's crust that these seismic waves travel through can also affect how fast they travel and how strong the shaking can be when it finally reaches you. So we need to understand and learn a lot of these different things about Earth's structure in order to know how strong the shaking will be. Another thing that, at least for me, I think is really interesting about earthquakes is that we can use them as a lens to learn more about the Earth. So sure, we want to learn more about the Earth so that we can mitigate our risk, but it also sort of goes in the opposite direction. One example of how we've done this maybe sort of recently is by looking at this special class of earthquakes called tsunami earthquakes. These break the very shallow part of a subduction zone. On the left-hand side is a picture showing a cross-section through a subduction zone. So that area where you can see it's labeled A, B, C, D, that's the oceanic plate that's subducting beneath the continental plate. The areas where it's labeled C and D are the really deep parts of the subduction zone. And the area labeled A is near the trench or the seafloor. Most of our earthquakes occur in these areas called B to C, so they mostly occur in the deeper parts of the subduction zone. But every once in a while, and really only maybe 6 times in the past 7 or 8 decades, we have these things called tsunami earthquakes, which break the very shallowmost part of the subduction zone only. And the really interesting thing about these is that they create much larger tsunamis than is expected for their size. So while these are hazardous, by learning more about them, we can learn a lot about, for example, the type of rock that is in the shallow subduction zone. And in the process, we can also learn how to improve things like our tsunami early warning systems to be more prepared. Other ways that we can use earthquakes to learn more about the Earth there are many of these. So I list just a few of these on the right. And these are ways that we use both small and large earthquakes to learn more about the Earth. So one thing is we can learn more about landslides from these. On the picture on the left is, from Professor Amanda Thomas here in the Department of Earth Sciences, who was studying the Rattlesnake Ridge landslide up in Washington pretty recently. She deployed a lot of small seismometers on this landslide and recorded a lot of small earthquakes. And by studying these earthquakes, you can learn things about the landslide. So how fast is it moving? Where is the surface on which it's sort of sliding? And this is really important for learning more about the shallow part of our Earth and about this hazard in particular. We can also use earthquakes to learn more about the deeper parts of the Earth and how it behaves. We can learn more about the structure of the Earth by studying earthquakes, whether they're large or small. We learn more about tectonics and how tectonic plates move. We can also learn about volcanoes and their eruptions through earthquakes. So volcanoes and eruptions often create small earthquakes, and so we can study these to learn more about these volcanic systems. We can also do things like improve our earthquake and tsunami early warning system. So instead, less on the theoretical side, this is more on the applied side in terms of how do we use this to help society. When we study these earthquakes, we can learn more about how do we make a better earthquake early warning system or a tsunami early warning system. So these are things that give us alerts on the order from seconds to minutes ahead of time saying that we're about to feel shaking or we're about to see a tsunami, and we can do things to prepare and keep ourselves safe. These are just a few, but there's a lot of other things that we can do to use earthquakes to learn more about the Earth. And then how do I study all this, or how does one study all of this? For me, how I got into it is that in undergrad I was actually a pure math major. So for a long time I wanted to be a doctor and realized that that probably wasn't for me, and continued to pursue my passion for math and physics. And then in one of my last years in undergrad, I took a geology class as an elective and found it really exciting and really fun and never turned back. And so I wanted to apply a quantitative background to something that I could look at and actually touch. And so I decided to go to graduate school in geophysics, where I discovered seismology and studied things both on land and under the ocean when it comes to earthquakes. And so what does one need in order to study this? So in particular for seismology, there's often a lot of math, physics, and programming when it comes to geophysics, but these are all things that you can learn. So for example, here in our department at the University of Oregon, we teach a programming class that's specific to the earth sciences, where we use real data sets in order to teach you how to code, and you'll learn not only how to code with these real data, but you can also make maps. And in addition to these quantitative skills, there are also a lot of qualitative skills and creative thinking that goes into this. So I think there's a little bit for everybody, and there's more than just geophysics, there's also a geology track. How about opportunities that exist here? I think we have a lot here. So we have majors and minors that relate to seismology, or the ones that relate to seismology are geophysics, geology, physics. There are a lot of others where you can major and still use the skills that you learn here to study these kinds of things that I've been talking about today. There's a lot happening on our campus when it comes to earth sciences, and in particular seismology. So there's the Oregon Hazards Laboratory. This is related to seismology, but also to wildfires that we have here. There's the Pacific Northwest Seismic Network. The Oregon section of this is run out of our department. This is where they manage all of the seismic stations in Oregon, and these are used not only for scientific purposes, but also for things like our earthquake early warning systems. We are also one of the partner institutions for Shake Alert, which is an earthquake early warning system in the US that's run by the USGS. And we have people in our department who study the methods for earthquake early warning as well as actually applying it and working with stakeholders in the state to best prepare for earthquakes and best know how to use these warnings that we get to keep ourselves safe. And there's also a lot of opportunities when it comes to research. So as an undergraduate here, you can do research in these different topics in our department. We have a really strong research presence in seismology, in geophysics, in volcanology, as well as a number of other earth science topics. We have facilities that faculty use for research that you can also get involved in pretty easily. For example, we have a seismometer pool in addition to the Pacific Northwest Seismic Network, so we frequently use this for our research, and we've had undergrads work with this in the past. We have lots of labs in the department. We also have computational facilities like the High Performance Computing Center on campus, and we use that pretty frequently. And in particular, in these days of remote work, this is something that you can do even from your home. I put a list here of other seismologists or geophysicists that do this kind of work. So if you have questions, you can always reach out to me, or you can reach out to these folks here as well. And this is also just to demonstrate that we really have a vibrant group here that's studying these things. That's all I have for today, and I'm excited to hear what you have for a Q&A.
Thank you, Dr. Sahakian. So we have a few questions that have come in, and I want to make sure that we get to those, and I think maybe I have some follow-up questions because I always do. But first up, Maya. Maya wants to know, how can some countries mitigate the risk of losing infrastructure or lives if they don't have the money or other resources to do so?
This is a very challenging problem. I don't think I have a good answer for this. I think this is definitely more in the realm of engineering, but I think that there are things that we can prioritize, for example, in order to mitigate risk. So critical infrastructure is one that's always really important, because if you don't, for example, have clean water after an earthquake, that's a large problem. If you have a lot of structures that are at risk for collapsing, that's a problem. So there are groups that work in these countries that do things like work with schools to make sure their schools are retrofit to keep our children safe. Or there's a particular desk that's actually used in a lot of countries, developing countries that lack resources, that can be used both in schools and in other places to keep people safe when you drop cover and hold on. So they're reinforced desks. And these are things that are a little lower cost. So it's by no means a perfect solution, but I think there are smaller steps that you can take on the way to doing this.
Thank you. Okay, so Josh wants to know, what are people doing currently to mitigate the risk factors from earthquakes in high density areas?
Well, I think that our building code is pretty important, and I think this is something that's always evolving. So as we learn more about earthquakes and seismic hazard, we learn more about what is the shaking that we can expect, and how well prepared are our structures and our infrastructure for this. So the building code will change based on what we learn. That's one thing that's being done. There's a lot of work, in particular in the Northwest, that's being done right now to protect our infrastructure. So in addition to just the buildings that we live and work in, it's also things that I mentioned, like our water systems, our roadways, our energy facilities. So these are all things that are focus of attention right now in terms of improving our infrastructure.
Yeah, I think this is a question coming from me, but the article that was in the that mentioned Seattle, the earthquake that would destroy Seattle, I think was a big red flag for so many people, and in particular getting that kind of media attention. I think spurred a lot of policymakers to make some big changes and some decisions around retrofitting things. And I've certainly, as a driver in Eugene and in Oregon and Pacific Northwest, I've seen a lot of that on our roadways. What kind of, I mean, I think that was sort of knowledge that kind of was known within certain circles in the U.S., certainly in seismology circles. How is it that kind of media attention, what has that done for attention paid to an earthquake of that magnitude that could do a lot of damage to a city like Seattle or Portland?
Well, you mean specifically what have we done for this,
or no? Like like how do you get that kind of media attention, and what does it do in terms of? I hate to use the word shaking things up, but here
Sure.
I am doing that to kind of spur policymakers, lawmakers, those who are in areas where they can, engineers, for instance.
Yeah, certainly.
To put some more emphasis and effort in these kinds of realms.
Right. Yeah. So one thing, for example, in the Northwest is that it's actually really on the order of several decades that we've known that this is a subduction zone. So before that, we didn't even know it was a subduction zone. So in contrast to California, where we've known for centuries that we get earthquakes there, it's a little different here. Mm-hmm. And so for a long time, this wasn't really something that was in the culture or our common knowledge. And so when media attention like this comes out, I think it's really important for bringing information to people. So the more information you have, the more power you have. And that gives you the ability to speak up. So to speak to your legislatures, whether they're local or at the state level, to say these things are important to me. How can I be prepared on an individual level? How can I help my community prepare? And what kind of policies and law can we put in place so that as a larger society or at the state or many state level, we can be more prepared? So I think the media is really helpful for bringing attention to that and mobilizing us, so to speak.
Thank you. Okay, so Tori wants to know, how does the growing climate crisis affect the severity and frequency of earthquakes?
So climate earthquakes are really related to, or large earthquakes at least, are related to tectonics. And this is something that's on such a large scale that it is not really impacted by things that are happening on the surface of our Earth. This is actually a really interesting topic because when we think about climate change, it's so impactful for us as humans as a society, but when we think about it, we're really just living on the very thin skin of the surface of the Earth. So all these things that are happening with climate are happening in our atmosphere and oceans and the very thin skin on the surface of our Earth, but it's not impacting the stuff that's happening much, much deeper in the Earth. So earthquakes are happening from 5 kilometers down to 100 or more kilometers down into the Earth. So the things, in this sense, it's not really impacting motion of our tectonic plates and the consistency that we get in large earthquakes that are related to tectonics. There are things that affect smaller earthquakes, so slightly related to the climate crisis. Fracking is one thing that's often seen relating to earthquakes, or anthropogenic activity on the surface in terms of water injection and withdrawal. That can cause more small earthquakes or even moderate ones. But that's, I think, slightly tangential and not directly related maybe to things like sea level rise, for example, so that sea level rise is not impacting the frequency of earthquakes that we see.
Okay, thank you. Lauren wants to know, do you think that there has been an increase in frequency and intensity of earthquakes because of man-made climate change? I think that's along the same lines. Are there things that humans are doing that are causing an increase in frequency or intensity? And you answer that to some extent, so if you want to move on, we can.
Sure, yeah, I can maybe just address it a little more in that there definitely is anthropogenic activity or human activity definitely is having an impact. But again, it's more in places where it's not necessarily these large-scale tectonic things. So it's not impacting the magnitude 9s or 8s or 7s that we get on our subduction zones or the California strike-slip system. It's really affecting areas that were either not active at all or very inactive when it came to earthquakes, so closer in the middle of the continent. And so it's not really impacting the tectonic system, but more the shallow systems.
Okay. And fracking, I would assume that drilling in like the Gulf or in Alaska or someplace like that, it might have an impact on some of those shallower earthquakes. Is that what I'm hearing you say?
Yeah, I'm not sure that it's the drilling necessarily, but it typically seems to be related to water injection and withdrawal. So things like natural gas, it's usually related to.
Awesome. Thank you for that clarification. Anil wants to know, could you talk more about the connection between earthquakes and tsunamis and ghost forests, parenthetically the loss of our forests, and global warming as it pertains to rising sea levels?
Sure. So to explain a little more about our ghost forests, earthquakes, and tsunamis, not all earthquakes make a tsunami. The kinds of earthquakes that make tsunamis are the ones that actually break the seafloor on the trench. So in those subduction zone earthquakes, the ones that move all the way up to the shallow part of the subduction zone and move the seafloor, those are the earthquakes that make tsunamis. The earthquake itself, ignoring the tsunami part, actually makes our land move. So I'll sort of use my hands as an example here, but imagine the oceanic plate is going underneath a continental plate. In between earthquakes, it's sort of pushing on the continental plate, and it causes stress to build up, but it also sort of makes the continental plate bend. So you imagine our coastline is sort of here where my knuckles are. So it's going up in between earthquakes. And then when the earth isn't strong enough to hold that stress anymore, it breaks very quickly. So the seafloor maybe moves up, but the areas over here that were going up in between earthquakes now goes down very suddenly. And this happens to be at our coast for the most part in the Pacific Northwest. So that means that areas that were above sea level now are below sea level right after the earthquake. And that's what seems to be creating the ghost forest that we have along our coast here. The fact that those trees were above sea level and then all of a sudden, very quickly after the earthquake, are now living below sea level a little bit, or at least within the tidal zone. And that's what causes these ghost forests. When it comes to the relationship between earthquakes, tsunamis, and climate change, with sea level rise going up, tsunamis, when they do occur, may have a larger impact because it means that the baseline location of the ocean or sea level is already a little higher to begin with. So that means that when you add the tsunami on top of that, you can sort of think of it like storm surges affect us a little more in hurricanes with sea level rise. It might inundate a little further, and it might change a little bit how much subsidence you see in particular locations, or it'll change how we measure that.
Thank you. Stephen wants to know, what careers are possible for someone with a seismology degree?
There's a lot. There's a lot of basic research. So in an academic environment, as at a university, this is maybe one of the things that we often think about first. You can always study things either at a university level. There are a lot of governmental organizations that do seismology. So the U.S. Geological Survey does a lot. The National Oceanic and Atmospheric Administration runs our tsunami early warning systems, and that's sort of related to seismology. There are geological surveys within the states that also need people like seismologists, geologists, geophysicists. So there's a lot of research that you can do there. There are a lot of applied careers. So for example, the oil industry is often a big one just because the skills and the methods that you learn in geophysics and seismology are always applied to the energy industry when it comes to things like that. But then there are also things that you can do related to risk. So for example, there are things called reinsurance agencies who insure your insurers, and they're really interested in seismic hazard and other kinds of natural hazards because it impacts what their returns are going to be and how insurance is structured. So both reinsurance agencies as well as just insurance agencies oftentimes need people to run these kinds of models. And then there are also more humanitarian organizations that hire people with seismology or earth science backgrounds. So for example, what I was talking about, the agency that goes into locations and helps retrofit schools or comes up with various things that you can do when you lack resources, they also hire people like earthquake engineers and sometimes seismologists. So those are just a few things, and I think there's lots of things I'm probably missing.
Thank you for that. Okay, so what are some research opportunities or activities that undergrads have either within your department or outside that you're aware of that they could potentially be involved in next year?
Within the department, people oftentimes have projects that we'd love to have help with undergrads on. So for example, I had an undergraduate working with me last summer looking at seismic hazard in the Bay Area. So in particular, studying properties of the soil rendered underneath areas where we live to see which areas might see stronger or weaker shaking. We've had undergraduates working on things like the Rattlesnake Ridge landslide or shaking in the Pacific Northwest. There are often a lot of projects related to that. I believe the Pacific Northwest Seismic Network sometimes hires undergraduates to do field work with them, so maintenance of seismic stations. There's also a lot of work with modeling tsunamis, for example, and volcanology even, which maybe isn't seismology, but there's a lot of other opportunities in the earth science department outside of just earthquakes for research. And then outside of this community, there are oftentimes internships with, say, the U.S. Geological Survey. There are a lot of times internships at places like these reinsurance companies that do work. Oil industry very frequently hosts internships, and sometimes there are local, maybe not local, but other nonprofits or research institutions that will have internships available.
Thank you. You mentioned the connection between seismology and volcanology. Can you talk a little bit about maybe some of the work that's done in the Earth Sciences Department between faculty members that cross those disciplines? Is there interdisciplinary work within the Earth Sciences Department that maybe even students would be interested in?
Sure, there's definitely a lot of interdisciplinary work. So, some volcanologists are more on the geological side of things. So maybe they're studying the properties of the eruption when it comes to the rock itself, or looking at past eruptions by studying our geology. Some of them are geophysicists in that maybe they use electromagnetic methods to study what's happening under our volcano system. Some are using more theoretical methods to learn more about that, so more of applied physics to volcanology, and we have sort of the same in seismology as well. And then there's definitely intersection between volcanology and seismology because, of course, these are frequently related. So frequently movement of magma causes smaller earthquakes, or one of our graduate students was recently working on a project with the earthquake that happened in Hawaii a couple years ago related to the eruption down there. So there's a lot of interdisciplinary work when it comes to those things, and faculty often work together. So I think there are opportunities for undergrads to get involved in these interdisciplinary projects as well.
Thank you. So let me make sure that I got all the questions. One of the things that I like to ask our guests when we have them on our podcast is actually about just other knowledge. So the U of O's websites, for instance, have tons of information, but sometimes we want practical information that isn't necessarily on a website. Is there a tip or a trick or a piece of advice that you would offer to a new first-year student that they might not be able to find on our websites?
Related to
anything. I mean, this is your opportunity from a faculty perspective to be able to share some wisdom. Yeah,
so I guess when it comes to the science side of things, the USGS or US Geological Survey website is really great. So they have a latest earthquakes page, So this is relating to seismology, where you can learn all about the recent earthquakes that have happened around the world, not just in our country. You can click on them to get summaries of what the tectonic environment is, what faults they think it occurred on, have there been landslides or liquefaction from it, are there likely tsunamis? So that's a great place to go. But in addition to that, they have a lot of good web pages on background topics on seismology and earth sciences in general. So the USGS does a lot more than just earthquakes, so that's a great place to go to learn about concepts. There are a lot of other organizations, like for example IRIS, which is the Incorporated Research Institutions for Seismology, or UNAVCO, which is like the geodetic GPS, so to speak, organization. So they have a lot of information on their websites. NASA has a lot of great academic information and data that you can download. So I think those are good places to go. Relating to non-academics, I'm not sure. I guess nothing pops to mind immediately about things. One thing actually that I will give a plug for is Google Scholar. So when you come to university, you're likely going to be doing many term papers. You'll need to be looking up published research, and Google Scholar is a great place to start. So it's just scholar.google.com. You can type in a keyword, a topic. You can even type in the specific title of a paper or an author. There are profiles, so many of us have a Google Scholar profile, and Google sort of collects all of the publications that you've had and put it there. And it even has a little box that you can click on to copy and paste the citation for that. So that's really nice, and I think makes life a lot easier when it comes to getting references for your papers. So I would definitely direct you to that.
That's a good tip. Thank you for that. So that's all the questions that we have coming in and all of the time that we have today. For you students who are watching us live, thank you so much for joining us today. For questions regarding this or any other introduction program, please visit our website at orientation.uoregon.edu, or you can email us at orientation@uoregon.edu, and you can always text us at 541-346-1159. If you submitted a question today that we didn't answer live, we will follow up with you early next week, but I think we got to all of those. So, but we will make sure that we get to all of the questions that came in today. And to you, Dr. Sahakian, thank you so much for your time today. I really appreciate all that you've done to help our new ducks learn about the breadth and depth of academic opportunities here at the University of Oregon. Thank you so much.
Thank you. It's been a pleasure, and hopefully I'll see some of you around campus sometime in the future.
I'm sure you will.